question one on this paper, we've got a question about waves. This one is about infrared waves. It tells us that infrared waves are transverse. Completing the sentence, in a transverse wave, the direction of oscillation is something to the direction of energy transfer. The answer that goes in there is that it's perpendicular. Okay, so perpendicular meaning the oscillation is a wave, so something going up and down, and the wave travels at a right angle or perpendicular to those oscillations that are causing it. The alternative is a longitudinal wave, in which case this word would be parallel, but that's the correct answer here. Now, first up, this is very first page, we've got a 6-marker question about a practical. However, don't be afraid, it's one of the easier practicals to remember. It's all about infrared radiation and its emission. So we've got, reading the question, we've got affecting how the color surface affects the rate at which a surface emits infrared radiation. We've got a silver colored flask, a black colored flask, and a kettle of cold water. And this is a bit unusual. This wouldn't come up in every single question about this practical. It says the hypothesis that black colored flask will emit more infrared radiation than the silver colored flask in 10 minutes of cooling, during 10 minutes of cooling. So you have to be specific with this question, refer your method back to this hypothesis, because that's what the question's all about. Now the method itself, the first bit, is relatively straightforward, okay? I mean, in terms of what you do with the kettle. So I'm going to write out in bullet points. I'll show you there's alternatives you can say along the way as well. So the obvious thing is that the kettle's got cold water in it. So we're going to heat the water using the kettle. Heat the water using the kettle. Then once that's done, we're going to add an equal or the same volume of water to each flask. Then what we're going to do, and I'm going to do this using a thermometer initially, because infrared radiation, we should know, is essentially to do with heat and temperature. So to measure heat during cooling, we're going to use a thermometer. So insert thermometer in each flask, and you're going to record the initial temperature, or the temperature before you start a stopwatch. Okay. Next, what we're going to do is the whole point of this hypothesis. It says 10 minutes of cooling. Okay, so we're going to start a stop clock. And I would always say stop clock or stop timer. It doesn't come up in mark schemes. It's always better to say start a stop clock. And then record temperatures after 10 minutes. Okay, now let me talk to you about the alternative here. The alternative is not to use a thermometer, but instead to use an infrared detector. Okay, so infrared detector can detect directly the infrared radiation being emitted. However, because we know infrared radiation is heat, we're then using a thermometer to kind of measure that indirectly. Okay, if you do use an infrared detector, you have to make sure it's the same distance away from each flask. Okay, now you do not have to mention both. Okay, you'll see on the mark scheme there are both. However, only one of them is necessary here. However, that's this so far what we've talked about has only probably got us about 4 marks. Okay, out of our 6, obviously we want to get 6 marks. So what have we got to talk about? Well, we've got to then talk about, well, how do I compare? How do I know if the hypothesis is right? So then you talk about how do I know which has got the biggest temperature difference. So we're going to calculate the change in temperature, and obviously that's for both flasks. And with the hypothesis, we would know that the largest temperature decrease would be the biggest emitter. Okay, so the largest temperature decrease, once you work out before versus after, will be what we're looking for. So you compare the flasks, and you say that the largest temperature drop or temperature decrease is the biggest emitter. Okay, so 6 marks in total for that question. It's one of the easier required practicals. However, like I said, read the question carefully. If it asks you to talk about something a little bit different or a bit specific, you have to mention it. For example, you have to mention 10 minutes because it says 10 minutes in the question. Okay, let's rattle through the rest of question 1. Next bit, it says, when will the flasks emit radiation at the greatest rate? During the first minute, fifth minute, or 9 minute? So the greatest rate means like the greatest amount of radiation per second. Now that's going to be in the first minute. If you were to draw a graph of these results, you'd find that the temperature over time, the graph would be quite steep initially, then it would start to become more constant as it becomes closer to room temperature. Okay, so what we'd say then is that during the first minute, that's when it has the greatest difference in temperature. So in temperature between the water, because it's hot water at this point, the water and its surroundings, or the air around it. Okay, so that's your second mark in that question. Okay, next we've got a bit of practical skills, and we're looking at a slightly different experiment. We're looking at someone this time talking about absorption of infrared radiation by different surface colours. It says the student filled 4 hollow metal cubes with cold water, each cube is the same size, so this sounds important stuff, but has a different surface colour. Then they'll place the same distance from an infrared heater, and it said the student measured the temperature increase of the water inside each cube. Now this question asks us for the dependent variable. Dependent variable means the thing that is measured, so what you're measuring in the investigation. So actually it's quite a lot of information here, which we're going to use some of it later, but the thing we're looking at is what they measure, which is the temperature increase of the water. Okay, so temperature increase is only 1 mark, so we're just stating what the temperature increase of the water. Next we've got the results. It gives us 4 different colours of the cube and their temperature increase after 10 minutes. Okay. Now we asked to make 2 conclusions. Okay. Now 2 conclusions, and it's really tempting here just to say, oh, shiny white has the lowest temperature increase and matte black has the highest temperature increase. I mean, those are 2 conclusions, but they're quite similar to each other. So for GCSE to really be thorough and get your marks, we're going to make 2 comparisons. We're going to make a comparison between the kind of matte and the white and black surfaces, and then also the matte and shiny surfaces. Okay, because those are 2 general things, rather than just saying, oh, this one's highest, this one's lowest. Okay, so what we could say in general then is that black surfaces absorb more infrared radiation. So more, I'm going to put IR here just to save room, IR than white surfaces. Okay, so that's my black versus white thing ticked off. Next we're going to talk about matte and shiny. So then we could say, well, matte surfaces absorb more infrared than shiny surfaces. So those are my 2 conclusions to make there. You don't actually have to mention data. It doesn't say to mention data, so we're fine without it. Okay, right, finish up question 5. We've got a little bit of information about one of these cubes. Tells us the dimensions of the cube itself. Asks us to work out the equation for force, area, and pressure. This one's on your equation sheet in the 2023 exam, so nice and easy. Pressure equals force divided by area. Now over here we're going to use it. It says the water pressure at the bottom of the cube is 1,500 pascals. Calculate the force of the water on the bottom of the cube. Okay, so there's a couple of things to do here. If you've seen my videos before, you'll know I like using the FIFA method to answer maths questions in physics, standing for formula, insert values, fine tune, and answer. So my formula from the previous slide, pressure equals force divided by area. Now we only have one number here. We only have the force. Sorry, we only have the pressure, beg your pardon. We're trying to find the force, so we know what this is. We don't know what the area is until we look over to this side here. So to work out the area, there's kind of 2 things to do in this equation. We're going to have to work out the area of a cube. So I'm just going to write this down the side here. So if you know how to work out the surface area, it is a square because it's a cube. It's just going to be 0.12 times by 0.12, which if you stick it into calculator, you can do it early on in the question to make sure you get the mark for it, equals 0.0144 meters. So let's put our values in. This is I stands for insert values. 1,500 equals F, which I don't know. You could write an X there if you wanted to. Divide by my area, which I've just worked out. So that's my 2 marks initially, 1 for that, 1 for this. Next, I'm going to find what F is. So I've got divide by 0.0144 at the minute. How do I get rid of that? Well, opposite of divide is timesing, so I'm going to times it by both sides, which gets rid of it from the right-hand side and puts it onto my left-hand side instead. So the last step to get your 4th mark is just to put that into your calculator. and it happens to be 21.6. So we write that in our answer line. 21.6 should be a nice, easy-ish 4 marks for that question. And that leads us to the end of question 1. So let me rate the different parts of it. So I'd say this is, we're going easy, medium, or hard. I'd say this bit's about medium, this page. A little bit tricky with calculation in terms of working out the area, but other than that, fairly standard. This one, I'm just saying it's hard because it caught a lot of people out. A lot of people didn't get 2 out of 2 marks when I marked this paper because they just talked about what the highest or the lowest. And that probably applies for this bit of the question as well. I'd say this part here is medium. 6 marker itself, I mean, I'm going to go with medium because I think it's one of the easier practicals. You need to learn the required practicals. However, it does have a bit of a twist with the hypothesis up there. Right, on to question 2, we've got a question about forces. It tells us about an airplane going down a runway. It tells us it goes from the airport terminal just outside it, down a runway to the finish line. And the question says determine the magnitude, that means size, just a fancy physics word for size, of the airplane's displacement from the start point to the finish point. Okay, now we should know displacement is kind of like distance, but it's in a straight line and it has a direction usually as well. So it's a straight line distance between one point and another. So for this part then, we are going to need a ruler and it actually tells us a scale in the question, so that might be another clue. Okay, so straight line from one part to another, we're going to go from start to finish, as is kind of hopefully obvious. So start to finish looking something like this. Okay, now for me that's about 7 centimeters. I think the official one in the mark scheme says 7.1, but I'm going to write down 7 centimeters. So 7 centimeters total, and there is a range for these kinds of questions, so you're always allowed a little bit either way. Now 7 centimeters, however, it tells us in the question 1 centimeter represents 70 meters. So therefore 7 centimeters times by 70 to make it into meters gives us here, would be, for me, it would be 490 meters. Okay, now the real answer, like I said, use 7.1 is 497, but this is within range, so that's totally fine. On to the rest of the question, we've got some forces labelled on the plane. It tells us air resistance, friction, and thrust from the engines, and asks us to work out the magnitude, again the size, of the resultant horizontal force. So horizontal meaning kind of side to side like this. So we've got thrust is one direction, so 14,000. Then the other direction, so we subtract it, these two added together, so 9,500 plus 4,500. Now you might not be able to need to put into your calculator to work this out. This one should be come out to being zero resultant force for that question. Now, as it's zero resultant force, we can then describe the motion. So how does it move as it goes along the runway? And it's just a describe question, not an explain question. Now, we should know if it's already moving, it tells us it's already moving, so it's not stationary. Really common misconception that if it was stationary originally, it would be stationary now. However, it's moving already. So if it's moving already, it's going to travel at a constant velocity or a constant speed. Okay. Don't say constant motion, I wouldn't say uniform motion here, constant velocity is what you're looking for. Okay. And 2.4, another one marker, it tells us air resistance and friction are both contact forces. Contact forces meaning forces that come into contact with another force for them to exert any force at all. Other contact forces, there's a couple you can have. So for me, the most normal, obvious one is the normal or the contact force. So when you push on something, it pushes back on you. You could also have tension. You could also have upthrust. You only need to give one. I'm just giving you 2 examples there to get your mark. Okay, next we've got some graphs to describe the plane's journey. It says the airplane stops for a short time, then accelerates along the runway, following this graph here. It says draw a velocity time sketch graph for this stage of the journey. Now, because it's a sketch graph, you don't need values on the y-axis. Okay, that's just there to make your life a little bit easier. So what it's going to look like is when the distance is 0, hopefully it's obvious the thing's not moving, so it's stationary at that point. Okay. Now, how do we draw stationary on a velocity time graph? Well, you've got to draw it with 0 velocity. So you kind of try and draw it, make it obvious that it's there, but a line along basically the x-axis. Okay, from 0 to 10. Next, it starts to move. Okay, so it starts to move. The distance is curving upwards like this. If it went straight up, it would be a constant velocity. However, this shows it is accelerating because it's curving upwards. Now, as it's curving upwards, on a velocity time graph, accelerating object just increases in velocity like this. So all you need to show for the second mark is that it's increasing in a linear fashion, where the curve looks pretty constant, so therefore it's accelerating in a constant manner. So we'd say constant acceleration. Okay, next one, we're going to talk about pressure. It says the height above the ground of the aircraft increases. Figure 7 shows how atmospheric pressure varies with height of the airplane. And it asks us to estimate the pressure when the height is 10. Now you might notice we don't have a point for 10, so we're going to have to do something a little bit different. So let's get our ruler out, draw a line best fit. Now, there's a really important skill to know, which is that if you look at the line, if it doesn't look like a straight line, i.e. here, you can see if I do it this way, most of the points in the middle are this side. It kind of looks a bit more like a curve. If it looks like a curve, then it usually is a curve. Okay. Now, lines of best fit, unlike in math, lines of best fit can be curves. So my top tip is to draw it kind of going away from you as best you can. So you're going to want to make sure it covers this 10 kilometers point, because that's where we are going to be looking to draw our point. So hopefully this will be relatively decent. I'm doing it quickly in pen. So let's say something like this. Okay, so a smooth line of best fit. Don't do them hairy, don't sketch it, don't do multiple lines. It should be one line. If you do it wrong, do it in pencil so you can rub it out and have another go. Okay. Now, once you've done that, then you're expected to then read off from 10 kilometers, so this point here, and always do it with a ruler, just so you don't mess up, because it's very easy to get messed up on graph paper and things like that. So with a ruler, you're going to measure off to the side and see how what the pressure is going to be, and mine is about 28 kilopascals. Even if you do line best fit wrong, you can still get this bit right. Make sure you show it from your graph how you've done it. Okay, and finish off question 2. Says what happens to the air surrounding the airplane as the height increases. Okay, so height increases, you're getting further away from the Earth's surface. Essentially, there's less air. So if we're talking about like what the different options are, temperature doesn't change, actually gets colder. Doesn't increase, sorry, it gets colder. Volume below it decreases, no, it doesn't make much sense. Mass above it increases, no. As you get higher up, the density goes down in this plane. Okay, so let's just talk about difficulty. I think that should be a relatively straightforward thing to know for question 2. I think people found it a little bit tricky to make sure it's a curve, but once you know that, I'd say both these things are probably medium. And this one should be an easy page, should be getting 3 marks for that page. This one, displacement, if you've learned how to do it well enough, the actual process should take you not that long. So that's question 2. Right, on to question 3. A little bit about forces again. We've got handbrakes in a car. It gives us a diagram with a pivot, a lever, and a force. The question says a driver applies the force as shown. The force produces a moment about the pivot. So moment, we should know, if you look at your equation sheet, moment equals force multiplied by distance. That's a clue for the next question. And the question says, how could the driver increase the moment about the pivot without increasing the size of the force? So obviously force can't be an option. The only way that moment could be increased then is by increasing the distance. However, we have to be really specific with our language here. It's not just about increasing the distance, it's about increasing the distance from the force to the pivot. Okay, so you can't just say increase the distance, you've got to say increase the distance from the force or where the force is applied to the pivot, or you could say the perpendicular distance from those 2 points. Okay, next we've got another velocity time graph. So we are going to look at after 3 seconds, the momentum of the car is 24,000 kilogram meters per second. Calculate the mass of the car. Which is a bit of an unusual question to ask about a velocity time graph. However, let's look at our equation sheet and see if we can use that to help us. So for GCSE physics, there's only one equation that has momentum in it. So the equation is momentum equals mass times velocity. Now for this part of the question, we are trying to find the mass, so that's what we're trying to look at. Momentum we know from the question. Velocity we don't know either, however it is a velocity time graph, that's our clue. Okay, so after 3 seconds, and obviously we're going to use the graph to help us because that's why it's there, we won't just stick it in there for no reason. We're going to go up from 3 seconds and go across, and we should find that we can find out the velocity. So use a ruler, nice and easy, up to that point there. Now this should be roughly halfway between 14 and 16, which means this is 415 meters per second. So now we know the velocity, that's the last thing we need to know to be able to work out our mass. So let's use our FIFA equation, and I'll always write down towards the side velocity equals 15, just in case you mess something up later. So we're going to use, like I said, FIFA or something similar to work out our final answer here. So momentum is 24,000. Mass we don't know, we're trying to find that out, so you can leave it as an m or an x if you want to. Velocity is 15. To get rid of times by 15, we've got to divide by 15, so divide both sides by 15, and that should give us an answer overall, if you put that into your calculator, of 1600 or 1600 kilograms. And it also makes sense. Mass of a car is roughly 1,000, 2,000 kilograms, so that's a reasonable answer. Okay. Next is the distance travelled during the first 5 seconds of the journey. Now, this one might be a bit trickier because we don't have anything here to do with distance. We could even start using this equation, but we might notice, we have time, but velocity is kind of changing. We can't use that directly as it is. So what we need to know then is that from this equation, the distance travelled is the area under a velocity time graph. I'm going to say VT graph, velocity time graph. Okay. So the area under it, sometimes a rectangle, sometimes it'll be a triangle, sometimes it'll be a curve, but either way you need to know that's how you find the distance from this graph. Okay, so during 5 seconds, we've got this section here, which is a triangle, and we've got this section here, which is a rectangle. So we are just going to need to work out the area of those two things, and I would always make it clear what you're doing so that it's easier for examiner to see. So I'm just going to draw out the shapes here. So area of a triangle is half times base times height. So for that, I'm going to use the base, which is 3 seconds. So that's 3, and the height is 15. And then I'm going to work out the rectangle, which is just base times height, which is 2 seconds, this lasts for, so 3 to 5 seconds, and it's at 15 meters. So stick those both in your calculator. You should find it's 30 meters for the rectangular part, and you should find this comes to 22.5 meters here. So mark for each of those, and then obviously it's the total 5 seconds, so you've got to add them up at the end. So 22.5 plus 30 gives you 52.5 meters. Now, worth just noting, there are no marks just for using this equation in that question. You've got to know the area and is the distance for a velocity at time. Make sure you revise that. Okay, on to the rest of question 3. So 3 talks about the distraction and braking distance. So the question says, in an emergency, the driver needs to apply the brake suddenly to stop the car quickly. The driver is distracted. Explain why the distraction will increase the stopping distance. So you don't get any marks here for saying distractions make stopping distance higher, but you can talk about, well, what makes up stopping distance. So the first thing to note is they've said stopping distance. Now we should know that stopping distance is made up from these two things. So stopping distance is made up from the thinking distance, or the distance taken while you're reacting, plus braking distance. So thinking distance plus braking distance, so that's showing you know what stopping distance is in a question, which is always a good idea. Now, which one is it that affects that affects stopping distance here? Well, it's the distraction. So what you'd say is that, well, actually, if I know that it's thinking distance, therefore it's stopping distance. So you're actually saying that sentence is enough for a mark in this question. Now, this comes up more times than people think. Let's talk about the relationship between distance and time and reaction time. Now, we should know, person going at a constant speed, essentially, if you have, there'll be, so essentially if time increases, that means there'll be increased thinking distance. So reaction time will increase. So the reaction time will increase, okay, before the driver applies the brake. So therefore, so the thinking distance will increase. Okay. Now, please make sure in questions like this, you're talking about things increasing, decreasing, not speeding up, slowing down. It's asking about distance, and then we're going to use the idea of reaction time to help affect that. You could say, you know, they're directly proportional if you wanted to for an additional question. Distance is proportional to time. Next part of the question talks about why the temperature of the brakes increases as they are used. So increasing temperature of the brakes, another question, you've got to be really specific with your language here, okay? So what we say is that there's friction, but not just friction, there's work done due to friction or overcoming friction in the brakes, okay? You can see in the mark scheme it says ignore friction by itself. There's work done. If you forget what that means, that's effectively the same thing as energy transferred. Okay, but work done is the phrase to use here, and that then means that there is an increase in the thermal energy of the brakes. Notice how they just talked about temperature, they didn't talk about energy or anything like that. So we're going to talk about the thermal energy of the brakes for our 2 marks here. So I'd say for that reason, I'd say both those actually to get 4 marks on are relatively tricky. Okay, so it might seem like easy questions, but I'm going to say the medium to hard, I'd say, for that bit of the question. The rest of this, again, I'd say it's probably medium. The graph, velocity time graphs, that kind of thing comes up relatively frequently, and this one should be an easy one once you've learned the definition for a moment correctly. Okay, moving on to question 4, and we've got our lovely magnetic field, and we've got a loudspeaker, which is pretty nice, and we also got a microphone. So we're going to talk about both of those in this question. Now the question says the microphone is used to convert pressure variations in sound waves, or basically sound waves, to variations in, and the idea is a microphone sends an electric signal, so it's variations in electric current. That is the purpose of a microphone. Speaker would be opposite. Okay, speaker converts current into sound waves, but we don't need to worry about that for this question. Next, we've got some magnetic field lines, and now we should know they always go from north to south. So let's have a look at which one of these always go from north to south. It's only one of them, really. It's only the top one where they always go away from north and towards south. We've got a definition next for an induced magnet. I'm going to write this one up here because I've not got room down here. Now, an induced magnet is a material that becomes a magnet, or becomes magnetic, or magnetized, sorry, that becomes a magnet or magnetized when in a magnetic field. Okay, when placed in a magnetic field. So the idea is here, it's just like a steel paperclip or something like that. It's got to be a magnetic material, has to be a magnet, otherwise it couldn't be attracted to anything. But it's only induced, so it's only temporary. Okay, right, next we've got a bit more detail about a loudspeaker. So loudspeaker is a permanent magnet. We've got signal from a microphone, and it says the speaker moves. It says, what is the name of the effect that causes the coil to move? So the clue is in the name moving. Anything that's to do with motion in magnetic fields is a motor. Okay, so it's the motor effect for this question. We've got a calculation question up here. The equation we're going to use from our physics equation sheet is force equals magnetic flux density B times by current times by length. Okay, I'm going to write those ones in because people can forget those. So B is the symbol used for magnetic flux density. So that's what's given to us in the question. So it tells us the current, tells us the force, tells us the length. We're trying to find that out. So classic case of using FIFA to make sure we get all our marks. And now before we do that, let's check are there any prefixes or anything we need to convert. Well, yes, there is. This 16 amps is the regular measurement for current. So I'm going to write this off to the side. 1 milli is equal 1,000th of an amp. So 1 milliamp is 1,000th of an amp. So therefore, if you divide by 1,000, 16 becomes 0.016 amps. So we can use that in our equation, but we've got to mark early doors. Okay, so force, we've got 0.013. Flux density, you can leave it as a B, you can leave it as an X if you wanted to. Current, I've just said 0.016. The length is 6.5. Okay, now there's quite a lot of things in this equation, so it's up to you how you want to do it, but you can work these two things out separately, at the start to kind of make your life a bit easier later on. You don't have to do that. I'm going to just divide them from this side, so to get rid of the timesing on this side, we've got to divide them from this side. I'm just going to leave them in brackets, but like I say, if you want to do that calculation first, then that is not a bad idea. So 0.016 times by 6.5. If you stick that onto your calculator, making sure you keep track of your brackets, etc., you should get this is going to be 0.125 as a magnetic flux density. Now, a little hint: magnetic flux density is always going to be a smallish number. Okay, it's quite a large unit, if that makes sense. So usually less than 1 Tesla. Could be maybe 2 or 3 tops, but it's never going to be like hundreds. Okay, next we've got a graph question, okay, which is something you can't really revise for, but I'm going to teach you how to answer a question like this. It says, megaphones produce very loud sounds. A person's hearing can be affected by age and by working in a loud environment. This figure shows how frequency affects the minimum sound level that can be heard by person A, person B, person see. And the question asks us to compare how different factors affect the minimum sound levels these people can hear. Now, for this question, there are 4 marks available, okay, which is huge for a graph question. So we need to be able to talk about several different things. Now, there's some obvious things to talk about. It is a compare question. So I'd say the most obvious thing to compare is the two 50-year-olds. One's worked in a loud environment, one's in a quiet environment. Initially, they have the same high frequency of sound that they can hear, but over time, with higher frequencies, the minimum sound level is higher for the person who's worked in a loud environment. So let's compare those two people first. So how are we going to do this? Lots of different things you could say is that a loud environment causes the minimum sound level heard. Sorry, I can't spell minimum. Sound level heard to increase with frequency. Okay, so that's one comparison. Now, I mentioned earlier, and any bits of data you can scrape about this graph is ideal because it's 4 marks. Actually, at 2000 Hertz, it's the same. Okay, so you could say, but at 2000 Hertz, the minimum sound level is exactly the same. So minimum sound level is the same. You could even say 24 for both loud and quiet environments. Okay, next comparison we could talk about is, well, next we've got to talk about line C. So this is about age, so hopefully it's obvious comparing the two quiet environments, so 50-year-old and 25-year-old. The 50-year-old has a higher minimum sound level of basically the whole range of the frequencies. Okay, so what we'd say is something like that the minimum sound level increases with age. Increases with age. Okay, and you could even put a bit more detail here. So you could see, e.g., increases the increase between 2000 and 3000 Hertz is larger with the 50-year-old than the 25-year-old. Something like that. So, for example, this part of the graph, all right, so there's a big increase there, not much of an increase here. Now, I'll be honest, that's pretty much enough for 4 marks, okay? You don't have to talk about every single thing on this graph. I'll just give you some options of things you also could talk about, which is, you could say about how after 4000 Hertz, the variation, the increase is very small in the minimum sound level that can be heard, etc., etc. But that will be absolutely fine for 4 marks, what I've said there. Please be aware though, you have to mention the axes on your graphs for this question, okay? You cannot just say, oh, the sound, or what can be heard, or damage in hearing. It's only a compare, you've just got to stick with what's said on the graph. And you don't have to worry about the arbitrary units, that just means, to give a context to the numbers, it's the minimum sound level that can be heard for that question. So for that reason, I'd say this is a relatively tricky graph question for a physics exam, because you won't see anything really like it before, and you've actually got to unpick it quite a complex way. I'd say this one here is medium if you know how to do FIFA. I think that's relatively straightforward. This one should be easy, and same with this part of the question too. Okay, question 5 is taking us to a fairground next, and we're talking about bumper cars. And we're going to talk about momentum and Newton's third law and things like that. First of all, it should be a straightforward definition by what a closed system is. It comes up in paper 1 as well. So closed system, there's a couple of ways of phrasing it, but essentially there's no energy transferred in or out of the system. So no energy transferred in or out, or the total energy is constant, or you could say, yeah, there's no, you could say it remains constant, you could say there's no forces in or out, okay, no resultant forces, either one of those is absolutely fine. Okay, I have to put these in brackets there. Newton's third law for this part of the question, it says, how does Newton's third law of motion apply to the collision between the bumper car and the barrier? It's only 1 mark this question, so it's not enough to just say Newton's third law, because it does say how does it apply. So it's 1 mark, but actually it's quite a long work to get your mark here. Okay, so Newton's third law essentially states that if you have a force acting on one object, the object will produce an equal and opposite force acting in the opposite direction. Now here it's talking about the bumper car and the barrier. So the idea is that the force of the car exerted or on the barrier is equal to the force of the barrier on the car, and in the opposite direction. Okay, so make sure you talk about the direction as well, not just the size of it. Okay, so equal and opposite, but it does say about those two objects, so you have to apply it there. Okay, next part of the question, we use physics equation sheet. We're going to use force equals, so it tells us the change of momentum divided by time. I'm just going to do the symbol form of this, which is change of momentum 700, time is 0.28. So once you've got the equation in there, this should be a nice easy 2 marks to breeze through. It's 2,500 newtons, which is a pretty typical value for force for a. Okay, right, let's go over the page. Now, this is such a common question. It comes up in lots of paper twos. It's all about how something kind of is flexible or not rigid, how it reduces the risk of injury or reduces the force or something like that. And it's always the same 3-mark answer. Okay, it's a really good one to memorize. Now, the risk of injury is always due to force. Whenever you see anything about someone getting injured or risk of injury, always keep in mind it's to do with force. And we're going to use that equation. So I'm going to stick this equation up here to help us. Now the idea is, generally speaking, in this equation, time is on the bottom of the fraction, so if I want to reduce the force, I actually have to increase the time taken. Okay, so let's put that into words. So you say increase the time taken for the collision, or for the collision to occur, okay, which is going to reduce the force on the person or the people. Okay, and you notice I've missed out a bullet point in the middle. This is because this is where the 3rd mark in here is slightly tricky to get your head around. Now, you can either talk about rate of change of momentum, or you can talk about acceleration. Okay, let's talk about rate of change of momentum. Rate just means divide by time, so it reduces the rate of change of momentum. But like I said, you could just as equally talk about acceleration here, because actually this equation comes from force equals mass times acceleration. Acceleration, we should know, is dependent on time. So if I increase that, I decrease acceleration, so that we are going to have a lower force overall. Okay, next question. Slightly tricky mathematical equation, because we've got to figure out the what we're going to use first of all. So car moves with initial constant velocity, and now it's accelerating at 2.0 meters per second squared. It tells us it travels a distance, so I'm going to write down my labels for what these things are. Final velocity v is this. The initial velocity is u. So I'm hoping once you've figured out those things, you should be able to figure out what equation it is. It is this one here, which is a firm favourite of GCSE students, I know, because it's just so easy to use. I'm joking. Anyway, right, so U we're trying to find out. V we know, so I'm going to still do what I normally do with FIFA, insert values, but the fine-tuning, the rearranging for this is a little tricky. So I'm going to slow down at that point to make sure we are all doing the same thing. So final velocity, I've just said is 2.5. Initial velocity, I don't know that, so I'm just going to leave it as it is. For now, I could write an X if I wanted to. The acceleration I do know, that's 2.0, and the distance is 1.5. Now, I thoroughly recommend with this question, like, do this bit first, basically, if that makes sense. So do your numbers times by each other first, makes your life a little bit easier later on. So on this side then, if I multiply those numbers together, 2 times by 2 times 1.5 gives us 6. And I'm going to leave this side as it is, just to add an extra step in there. Okay. Now, we're trying to find what u is, and it's currently subtracted from this side. So actually what I have to do is to add it onto this side to make it positive, because we're trying to find what positive it is, and then it gets rid from here. And to get rid of the 6 from this side, what I've got to do is subtract that from this side. So the u squared and the 6 kind of switch places. So the last thing to do then is to do 2.5 squared minus 6, which should give you u squared, if you put that into your calculator, will give you 0.5. However, that's not the end of the story, because we've got a squared function here, so we're going to have to square root it. Okay, so square rooting, sorry, beg your pardon, 0.25 on this side. So square rooting overall equals square root of 0.25, which, sticking in your calculator, if you don't know, is 0.5 meters per second. And that's the end of question 5. So let's have a look how we rate that. I'd say this is a relatively tricky equation. I'd say this is medium. You need to revise that. Okay, it comes up in mark schemes a lot. I'd say this side though should be relatively straightforward. Okay, a couple of definitions and a very easy mathematical equation. Right, on to question 6, which is a space question. Objects that orbit a planet, fact you need to know, are called satellites. They do not have to be natural, it could be moons or like the Space Telescope. Next we've got an equation, and we've got frequency, and we've got wavelength. We're trying to find frequency, so we've got wavelength and wave speed. So we are going to use the equation wave speed equals frequency times wavelength. That's a weird looking lambda. I'm going to just write down the equation form. Please do it in standard form, it means you're less likely to mess up rather than writing out loads of zeros. But before we do that, we should spot this is in centimetres, so 12.5 centimetres, just write it down on the side somewhere. In metres is going to give you 0.125 metres. Get your mark in nice and early for that. So we've got a mark just for inserting our values here. Next we're going to do a little bit of fine tuning, so I'm going to get rid of a times by 0.125 by dividing both sides by it to make it disappear from this side, and it comes over on this side, which we can put into our calculator. Once we do that, then we should find that it's going to equal, and depends on if you have a scientific calculator or not, it might do this already, 2.4 times 10 to the 9. If it doesn't, the question does ask you to put it in standard form, so you do need to put it in standard form at the end. But like I said, your calculator might do that already, so that's a nice, cheap, easy mark. Okay, right, this question comes up a lot, okay, about circular motion and things that are orbiting. It says, explain the effect of a gravitational force on the motion, so it's movement of the satellite, or the telescope, beg your pardon. Okay, so question, circular motion, it's always the same sort of answer. You've always got to talk about acceleration, you've always got to talk about the velocity and its direction. Okay, so we're going to mention those all three in one answer. So the gravitational force, so the force causes the telescope to accelerate due to force equals mass times acceleration. You don't need to mention that necessarily for the mark here. So causes it to accelerate. So this changes the direction because it's going around in a circle, so it's changing direction kind of continually. Direction of the telescope. And then lastly, well, how does that affect anything else? Well, actually, we should know that velocity is speed with a direction. So we say, so this changes the velocity. It's velocity. Okay. Now, I've seen lots of questions which are kind of like that or in reverse. So they ask you to talk about its, I don't know, how will the circular motion cause there to be a force? So in that case, it'd be the direction changes, so its velocity changes, so it's accelerating. Okay, right, on to 6.4. Okay, this question is a little bit trickier, right? Now, this is all about, and it even says in the question about like what happens to the wavelengths, but let me explain this question a little bit. These are called spectra, okay? Now, this question do with redshift. Now, redshift, you should know, it's not just going to be one of those questions where it's like, oh, the light is more red, because that's not what actually happens. What actually scientists and astronomers measure from distant galaxies and stars is these things called spectra, which are essentially all the colours of the rainbow, and they have some colours missing depending on what those elements are in those galaxies or stars. Okay, they don't talk about too much for now, but that's just a bit of background what these things are. You just need to keep an eye on, well, what has happened to the wavelength. So for the sun, we see it's got the wavelength like here, and then for reference, then we've got Galaxy A has got increased wavelength, Galaxy B increased, but not quite as much. It says what conclusions can be drawn, and it's also got an explain part to the question as well. So what we'd say then is that, and I've mentioned it up here, is that both essentially Galaxy A and B are both redshifted. Okay, so we say Galaxy A and B are redshifted or have redshift. Okay, but as I said, A is further, so we say A has a greater redshift. Now, what does that mean? This is where the explain comes in. Okay, so what that means is if it's greater redshift, it's traveling. So A, sorry, is traveling faster than B, and A is further away than B. Okay, that's what redshift tells us in this question, that velocity, the farther away they are, the higher their velocity is, generally speaking. So a really interesting redshift question on that. Okay, so I'd say this one, probably medium to hard, possibly a harder question, but if you have bispectra, that should be okay. I'd say the rest of this also is medium. It's a medium-ish short calculation, and this stuff comes up a lot, so make sure you learn the mark scheme for this part of the question. And this one should be an easy, just a simple definition to start off that question 6. Okay, over the page to question 7. This question is all about light. Okay, so light, big part of paper 2. First question, it says what name is given to reflection from a smooth surface? That is called specular reflection. So specular means that light comes in and goes out at the same angle, as opposed to a rough surface where it would go in and kind of come out at odd sort of angles. So specular reflection from a smooth surface. Now, for the conclusion that could be made here, we need to look at the mean. So this is the angle of reflection, the angle of incidence. The conclusion is that the angle of incidence, if you look at each value, you should notice they're the same. So we say angle of incidence equal to angle of reflection. Okay, don't say the proportion or anything like that. Those two columns are exactly equal. So we say they're equal to each other. Next one talks about type of error causing a variation in results for angle of reflection. Now, type of error, if you ever see a question like that, it's basically a 50-50. Okay, it's either random or systematic error. Okay, now random error happens that causes variation in results, causes variation to go up, down, results go up, down, higher or lower than what they should be. Systematic affects results in the same way each time, so they be basically a bit higher or a bit lower than what they should be. So it affects results in the same way. Now for this one, the variation is kind of, I don't know, a bit higher, a bit lower. You've got 8, 10, 11, 21, 10, 20, etc., etc. So it is a random error. And this practical, there's a very clear, and you need to learn the random errors for all the practicals really. But for this practical, what causes random error is going to be, I think the easiest bit, is when you're measuring the ray of light, you essentially don't know where the center is because it's quite thick. So I'd say the center of the ray of light may not have been marked correctly, or may have been inaccurately measured. Okay. You could say things like parallax error here as well if you wanted to. So parallax error, if you're measuring the protractor, you might be measuring it slightly to the side of where you should be. Please don't say things like measured it wrong, stuff like that. Okay, you've got to be specific with your answers. Okay, right, for this question, 7.4, why has it not occurred? There's a couple of ways of saying this. You could say all points of the wavefront reach the glass at the same time, something like that. An easy one to say is that the wave or the ray is along the normal, something like that. But I would learn the top one because it comes up in other types of questions when you're talking about, I don't know, let's say a wave hits a boundary. The idea behind it refracting is that one part hits before the other, so it's worth learning that one. Okay, working out the next one, this one's a little bit tricky one. It says they recorded 4 different angles of incidence. Now you might be able to see, looking at the protractor, that they can't record those. Okay, now the reason is because they've got an extra decimal place than the protractor has. How we'd say that in a good scientific term is we'd say, talk about this idea of resolution. So resolution is the smallest thing, smallest measurement a piece of equipment can make. Now for a protractor is 1 degree. So resolution for a protractor is the smallest thing it can measure is 1 degree. So it goes up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so therefore, so it couldn't be used or can't be used to measure 1 decimal place, or one decimal place, probably the easiest way of putting that. Okay. Right, over to question 7.6 to finish off this one. Right, I alluded to this earlier. Okay, it says in terms of wave fronts, the wave fronts are these lines here. Why does refraction happen at the boundary between air and glass? So you've got to try and imagine this going towards the glass. What happens as soon as the wave reaches the boundary? So it should be able to spot that this part will reach it first, so that will slow down first. This part will reach it second, so actually you'll carry on going at the same speed, and that whole effect causes the wave to change direction. Okay, so we'd say something like this, that different parts of the wavefront reach the boundary at different times. Okay, specifically, so you'd say the top part, the left-hand part, it doesn't really matter. So the top part of wavefront reaches after the bottom part, so slows down. So this is where the speed comes into it. So slows down after the bottom part. Okay, so I've used the term top and bottom here. You could use left and right if you're talking about here, but as long as you are really clear with what you're talking about in this diagram, that's what you're talking about. Okay, and the idea is it slows down because glass is a more dense material. Okay, so for this question, I'm going to say this bit's probably a medium. Okay, good one to learn, good one to memorize. I'd say this one's quite a hard one to get your 2 marks on, but definitely learn what the word resolution means. That one should be kind of straightforward. And earlier in the question, I'd say this is medium. I'd say these two should be easy. These two should be things you can get with just 1 mark. Nice and easy for question 7. Okay, over the page we've got a question about transformers. Now there's actually not lots of detail on transformers in this in this paper, but it talks about the material used for the core of it. Now we should know they're made of iron, so they've got an iron core, and the reason is you could say it's easily magnetized, or it is a magnetic material. Okay, so it's easily magnetized, or you could say it's a magnetic material. Okay. The idea is it's able to, the magnetic fields that's produced here are able to kind of be transferred through the core quite easily. All right, next we've got 8.2, a calculation. We've got a power of the transformer along the secondary coil. It talks about efficiency, and it asks you to determine the current. Okay, now where are the others? Well, there are values over here, few. We've got some values on the number of turns, we've got some values on the voltage or potential difference. Okay, now you might be able to spot this straight away, but because this is 5 marks and there's no marks for units or significant figures or anything like that, this is a multi-step equation. Okay, so multi-step meaning we are going to need to use 2 different equations to work this out. Okay, so let's just write down, brainstorm some equations. So there's a couple of transformer ones. So there's one involving voltage and current. So we could write down voltage times current of the primary coil equals secondary coil. So I would always write these down just in case you lose track and forget one later. We've got the number of turns. So number of turns on primary divided by secondary equals the voltage across primary and secondary. Power, there's a couple of equations for power. We could do, I don't know, I squared R, we could do I times V. Okay, so maybe just write these down the side, then you can use those to figure out which one is going to be most helpful later. Okay, now we're going to use this one here. Now, first of all, if you were to look at this part of the equation, number of turns, I've got primary and secondary, and I've got the voltage across the primary as well. Okay, I've written it down wrong here. Sorry, that should be a V. So I'm trying to find that I could find the voltage on the secondary coil. Is that what I'm trying to find out? Well, no, but it will help us find that. So if in doubt with a question like this, just work out something correctly, and it will help you a bit later on. Okay, so let's write down my values. So the number of turns on the primary coil divided by secondary coil equals the voltage, or PD, across the primary divided by the secondary. Real nightmares with this VS today. Okay, so primary divided by secondary, and so look at my diagram, is 2000 divided by 40. The voltage on the primary is 230, and this is Vs, which I don't know. You could write an X there if you wanted to. Okay, so depending on how you want to do this, I quite like flipping fractions with these kinds of questions. You don't have to. Basically, if you flip, because it's on the bottom, you're trying to find it on the top to make it a bit easier. If you flip both sides of the fraction, it's the same thing, so it might make your life a little bit easier later on. You don't have to do that bit though, but once you've got this kind of all in place, hopefully you should figure out that the final equation for Vs is going to be 40 divided by 2000, or you could do that bit first if you wanted to, and then times by 230 to get rid of the 230 from there. Okay, now either way, voltage for that should come to 4.6. Now that isn't our final answer, however, that does get us 3 out of our 5 marks already, which is not bad going. Okay. Now, if you need more extra room for this, I would always use the space down here or space in the back, top tip. But this time we're going to try and find the current. Now, what have we not used yet? We've not used the power. So let's try and figure out how we could use that. Now, we're going to use this equation here. Power equals current times by voltage. Because we've got the power, now we've got the voltage across the secondary coil, I can work out the current. So P equals I times V. Power is 6.9. The current, I don't know what it is, so I can write an I or an X or something like that. And the voltage is 4.6. Okay. Now to finish off, what we're going to do is to just get rid of our times by 4.6. So 6.9 divided by 4.6. You stick that in your calculator, and you should get that comes to 1.5 amps. Okay, and that's your multi-step equation. Now I'd say because it's multi-step, I always think these things are relatively tricky. I think that's not too bad one. This bit though should be relatively straightforward for the start of question 8. Okay, let's go over to the last question to finish off. It's about magnetic fields again. I say this to all my classes, revise this stuff. It comes up a lot. It's always one of the last questions when you're going to be really tired in the exam. Get like a perfect 4 or 5 mark answer for how motors work, for how generators work, and then you won't need to think about it, you'll just rattle off your tongue. Okay, so it talks about a dynamo here, which is a little bit of a different type of question. Used to generate an electric current. Shows the parts of it here. It says the coil is rotated. Explain why a direct current is induced in the coil. Now we should know a dynamo, if you watch my video on this, it will genuinely help quite a lot. Dynamo, there's 2 types of generator basically. There's an alternator and there's a dynamo. Okay, now generator meaning it generates electricity. Now the clue is D dynamo gives a direct current, A alternator is alternating current. Okay, but it's essentially the first part of your answer is going to be basically the same answer you'd give for any generator. Okay, now the part I mean is this comes up in mark schemes all the time. Okay, so what you'd say is that the coil moves or cuts through the magnetic field. Okay, so just saying it moves through the field, easy, job done, 1 mark. Okay, and then what happens, it tells us a current is induced, but before there's a current flowing, there has to be a positive and negative or potential difference induced. Okay, so what you'd say is that a PD is induced, you've got to say the word induced there, across the coil. And why does current flow? Well, current is flow of electrons. If there's a positive and negative, the circuit has to be complete for the electrons to flow around. Okay, so as it is a complete circuit, current will flow. Or current is induced. Okay, now that's a standard 3 mark answer. Okay, however, for the rest part of the question, we're going to explain why it's direct current, because normally it will be alternating current, so something has to happen for it to be direct current. Okay, now in this question you might spot there is a commutator, which you'd normally find in a motor effect. Okay, however here you'd find it in a generator. Okay, so let's finish off last 2 marks of this answer. We're going to talk about why there's direct current. Okay, now what the commutator, what it does is each half turn or half revolution. Okay, essentially the contacts are going to be switched over basically. Okay, so you'd say the 2 brushes of the commutator are switched over. Okay, so therefore as a result you'd say so the direction of the current or the PD doesn't change direction. Okay, that's the standard bit 1, 2, 3. This is the bit that deals with why it's direct current. Okay, that's specific to a dynamo, so definitely memorize that. If dynamo came up again this year, you know what you're talking about with that part of the question. Okay. Right, next one we're going to plot a graph for potential difference. Now we know it's direct current, so therefore it's not going to go positive, negative. However, it is not just a flat line. Okay, direct current in a battery goes like this. However, like I've kind of drawn out here, essentially what happens is it goes up, down. Instead of going to the downward part, okay, it goes up again. It kind of gets reflected in the x-axis. So something like this. Okay. Now I've realised just drawing this, I've done a very bad thing. I've not done it in pencil because actually it asks for 2 complete cycles. Alright, so I'm going to do it again in a better colour pen. Alright, so slightly ignore that one. It's the same thing, I'm just going to do slightly smaller because it asks for 2 complete cycles, which is 4 bumps basically. There we go. Learn from me, do it in pencil and the real thing. Okay, so this one, not the other one. That's the reason it's 2 complete cycles is because it goes bump, 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 bump. However, you're reflecting those 2 in the x-axis. Right, this is one of the hardest things you could be asked for. It is on your specification. It's basically A-level physics. It says the lamp is disconnected. Why it becomes easier to turn. So the lamp's disconnected, essentially, there's no current flowing. Okay, so that's the easy mark in this question. There's no current flowing if the lamp is disconnected. Okay, now how does that affect it? Well, we need to know that when there's current flowing in any coil of wire, there are these tiny magnetic fields around it. Okay, so what we'd say is there's no magnetic fields or field around the wire. Okay, now what that magnetic field does is it opposes, to go the other way, oppose is the best word to say here, to oppose the motion or the movement of the coil. Okay, so for full explanation of this, I'd strongly advise, for full explanation of this, I'd strongly advise going to watch my video about magnetic fields. Okay, I'll explain it in a bit more detail. Okay, right, hope that was useful. That's paper 2, 2023. Just to finish off, I'd say this whole page, you will find it hard. However, you revise generators and you revise motors and things like that, it will become much easier. But I hope you found that useful. Thanks very much.